Dear student, today I'm going to explain about more types of LR parser. The one which we discussed in the previous one, shift reduce parser, which is also a bottom-up parser. You know that there are two types of conflict occurs during the parsing of shift reduce parser. One is shift reduce conflict, the other one is reduce reduce conflict. These things are occurred because the parser will not be knowing that when to shift or when to reduce. To overcome from that problem, we use this LR parsing techniques. So there are many ways to do that, and it also covers wide range of grammar. One is SLR, that is it's also called as simple LR parser. The next one is LR, that is most general LR parser. The third one is LA LR parser, which is looking ahead for an input symbol. And all these three parser will work in the same fashion. That is, the algorithm remains same. The only difference is how you are going to construct a parsing table. So now coming to this particular parsing techniques, so which uses a stack which holds an intermediate result, and the input buffer which holds the input string to be passed. And then as I said, LR parsing algorithm. This algorithm uses input string, then the stack and the parsing table. Using all these three, it passes the given string and it gives the output. That output is nothing but either to shift or reduce operations. Now today, I'll be explaining about how to construct a parsing table. Then later we'll discuss about how to parse a string using this LR parsing. So coming to construction of SLR parsing table, it's also called as simple LR parsing. So it's also called as LR of zero item, because where L stands for leftmost derivation, R stands for rightmost, L stands for reading the input from left to right, R stands for rightmost derivation, 0 is for looking ahead for zero input symbol. So coming to this, we call it as LR of zero items. So what is this LR of zero item? It's nothing but, so an LR of zero item of a grammar G is a production of G, a dot at some position of the right hand side of the production. So it means that you will find a dot on the right hand side of the production. So for example, if you consider this particular grammar, A tends to A, B, B. Now my LR of zero item for this particular given grammar look like this. The possible LR of zero items are, one is, the first we'll put this dot, that is nothing but A tends to dot A, B, B. It means that I'm looking for A, B, B. It means before the dot, whatever we see, that is we already read it. And after the dot, whatever we are going to see, that is nothing but what we are going to read, which is left out for reading. So it means that the next thing is, so A tends to A dot B, B. It means we read already A, but we are going to read B and B. Similarly, A tends to AB dot B. It means that we read already AB and we are going to read B next. And the third, last one is A tends to AB, B. It means that, so this has been read already. So when you find dot at the end of the production, it means that this is ready to reduce it. Now here, there is no confusion of when to shift or when to reduce. It means that whenever you find a dot followed by A, it means that you can shift this A onto the stack. Whenever you find dot at the end, it means that this has been read already. So these things, when you find A, B, B followed by a dot on the right hand side of the production, it means that this is ready to reduce. It means that it can be reduced to E. That's the meaning of LR of zero items. So in this, when you are constructing the parsing table, first of all, you are supposed to find this LR of zero items, and then we are supposed to construct a parsing table. So in order to do this, we say that an augmented grammar. What is an augmented grammar? G dash is a grammar G with a new production, that is S dash tends to S, where S dash is a new starting symbol. That is, we're going to add G with a new production, S dash tends to S. So where S is the start state of the G. It means that now the G dash becomes my augmented grammar. The meaning of adding this particular S dash tends to S, it means that we have reached S as the top of the root of the tree. That's why it is called as S dash tends to S is a new production has been added. This is done to signal to the parser when the parsing should stop to announce acceptance of the string. As I said, S dash tends to S is added. When you reach S dash tends to S dot, it means that you have reached the top of the tree. So there are two functions to construct this parsing table. One is the closure, the other one is the goto. So we'll define what is closure and what is goto, and also we also call it as it's a collection of set of LR of 0 items. It's also called as a canonical collection of LR of 0 items. Is a basis for constructing the SLR parser. So it means that, so in order to construct this SLR parsing table, it is required to find out LR of 0 items, and this can be done with the help of closure and goto function. So let me define what is closure operation. If I is a set of LR of 0 item for the given grammar, then the closure of I is a set of LR of items constructed from I by the two rules. What are those two rules? See, if I consider I is a item of the grammar G, then I'm supposed to find the closure of I. What are those two rules? Initially, every LR of 0 items in I is added to the closure of I. Initially, whatever it is there in the LR of 0 will be added into the closure of I. And then if in case of this particular item set, if you find if A tends to alpha dot B beta, you can carefully observe if A tends to alpha dot B beta is in closure of I, then B tends to gamma is a production rule of G, then B tends to dot gamma will be in the closure of I. It means that whenever you find A tends to alpha dot B beta, then B is a non-terminal symbol, then all the production of B into this closure of I. It means that by adding the dot at the beginning of the particular production which belongs to B will be in closure of I. We'll apply this rule until no more new LR of 0 item can be added into the closure of I. So if I started with this particular I, we keep on adding these items. See, for example, B tends to dot gamma. If once again this gamma is a non-terminal symbol, once again we'll add all the productions of gamma into this particular set. So we'll keep on adding this until we find no more elements to be added into this particular closure of I. So the function looks like this. See, for example, function closure of I, begin, j is equals to I, repeat. What you're going to repeat? For each item, A tends to alpha dot B beta in J. If you find a production of this type in J, and each production B tends to gamma of G, that is, if B is a non-terminal symbol, then such that B tends to dot gamma is not in J. If it is not there in the J, you can add that B tends to dot gamma to J, and until no more item can be added into this. So if at all if B tends to dot gamma is once again gamma is a non-terminal symbol, we repeat the same thing. We keep on adding the element until we find no more elements will be added into this particular J. That's why that is called as a closure of this particular item. So for example, this is the grammar given. As I said earlier, this is actually the grammar given, and then we have added a new production, that is E dash tends to E. So then this becomes an augmented grammar for the given grammar. So I'm supposed to find closure of. So I'm supposed to start with this is my LR of 0 item, that is the first item, that is closure of E dash tends to dot E. So it is of the type A tends to alpha dot B beta. Now my B is nothing but E. Then what I'm supposed to do is I'm supposed to add all the productions of E by putting dot at the beginning. Now my production for E is E tends to E plus T. So what I'm going to do is I'm going to add E tends to dot E plus T. Once again, this is A tends to alpha dot B beta. Once again, my B is E. What I'm going to do is I'm going to add E onto this. So once again, E tends to dot T. Once again, my B is once again a non-terminal symbol. So then I'm supposed to add all the productions of T. That is, I'm going to add T tends to dot T star F. Then I'm going to add T tends to dot F. Once again, my F is a non-terminal symbol. Then what I'm going to do is I'm going to add F into this particular set. So F tends to dot E, open parenthesis, E, close parenthesis. You can just observe that since it is open parenthesis a terminal symbol, you need not to add any production into this particular set. But I'm going to add one more production of F. F tends to dot ID. Since ID is a terminal symbol, you need not to add any more production into this. So this is what is called as a closure of E dash tends to dot E. Similarly, we do it for every production in the given grammar. So once we do this closure, then we are supposed to find the goto. So this, keeping this as a closure, we use the goto operation. What this closure and goto will help us in creating an automata which will inform us whenever there is a next input is seen, what is the next state we are supposed to move. If I is a set of LR of 0 items, so we have identified LR of 0 item, and X is a grammar symbol, that is a terminal or a non-terminal symbol, then goto of I comma X is defined as follows. If A tends to alpha dot X beta in I, if at all if you find a production is of type A tends to alpha dot X beta in I, this X may be a terminal symbol or it may be a terminal non-terminal symbol, then every item in closure of A tends to alpha X dot beta will be in goto of I. So please observe that once I read this particular symbol, that is dot followed by X, it means that I'm going to read this X. Once I read this X, I'm going to shift this dot from this position to the next position. It means I have read this X, so that's why I'm moving from A tends to alpha X dot beta. Once again, if this beta is a non-terminal symbol, then I'm supposed to apply the closure of this. So this is how I'm going to find out the go-to for every symbol from the given LR of 0 item set. For example, in the given grammar, my first I is E tends to. So you can just observe that we have identified this particular LR of 0 item. For that, I'm supposed to apply the go-to. So when I say that go-to, then I'm supposed to consider what it says that for each symbol, that is each symbol which is present after the dot, I'm supposed to find go-to of, I consider this particular state as one particular state on a particular symbol. I'm going to move to the next position. So it means that go-to of I, that is nothing but I on E. I on E, what it does is wherever you find E as an input symbol after the dot, you consider all those things. So where you have E dash tends to, you have a dot followed by E. So I'm going to move from E dash, E dot. Why I'm getting this E dot? Because I've read E. That's why I'm shifting this dot to the next symbol. So any other production where you have the dot followed by E on the right hand side, you have one more production where you have E tends to dot E plus. So once again, you will consider this also as go-to of I comma E. So it becomes what? E tends to. So I'm supposed to shift this dot onto the right hand side. E tends to E dot plus T. So no more production which is starting with E on the right hand side. So next symbol we are going to consider is T. When you consider T on the right hand side, which is having a production dot followed by T, there is one production where it have T tends to dot T star F. So what we do is go to of I comma T, that is E tends to T dot star F. There is one more production that is E tends to dot T. Once again, you have added that production E tends to T dot. So since we are not using any closure, because all the symbol which are finding after the dot are either the terminal symbol or there are no symbols after the dot. So when it comes to the go-to of I comma F, I'm supposed to consider each and every symbols which are we move from this state to the next state. When I consider this F, so then I find the F which is there on the right hand side, that is T tends to dot F. So I'll be converting this T tends to F dot, because after reading this F, I'm going to move to the next symbol. Similarly, I have a open parenthesis followed by the dot. So then I'm supposed to consider the go-to of an open parenthesis. So when I consider go-to of I and open parenthesis, I'll find that production whereas have the open parenthesis on the right hand side. So it means F tends to open parenthesis dot E close parenthesis. So you can just observe that after dot have a non-terminal symbol. So what I'm supposed to do is I'm supposed to find the closure of this. So what is the closure of this? That is closure of dot E. Then I'm supposed to add all the productions which is having E on the left hand side. That is E tends to dot E plus T. That is the original production given. E tends to dot T. Once again, I have a dot T. Once again, I'm supposed to add the productions of T into this. T tends to dot T star F. Once again, T tends to dot F. So since F becomes a new non-terminal symbol after the dot, once again, I'm supposed to find the closure of that. So I'm going to add the production of F once again. That is F tends to dot open parenthesis E close parenthesis F tends to ID. So you can just observe that this go-to, what you are supposed to do is you're supposed to consider the symbol which is there after the dot symbol. For all these things, you're supposed to write the go-to. Now the last one which is there on the right hand side after the dot is ID. So once you read ID, you're going to move from F ID dot. It means that after reading the symbol, which is the next state you are going to move. So we call it as, we call these new set is called a new state. Let us look at how to construct the canonical collection of LR of 0 items. To create SLR parsing table for the given grammar G, it is required to create the canonical LR of 0 item collection of the grammar G dash. Please observe that for the given grammar, we use G dash, that is augmented grammar. The steps are as follows. The algorithm says that find the C is a closure of S dash tends to dot S. So we already constructed this S dash tends to dot S. How to construct this closure, I've already explained. Once you are ready with this particular closure, repeat the following until no more set of LR of items can be added into C. So finally you get C, it's a canonical collection of LR of 0 items. For each I in C and each grammar symbol X, that is whatever the elements you have in this particular C, and for each symbol, if goto of I comma X is not empty and not in C, if it is not in C, what you're supposed to do is add goto of I comma X to the C. So C is a canonical collection of items. So what we do is we're starting with this particular grammar, that is S dash tends to dot S. For that, whichever the symbol you have in this particular S dash tends to dot S, we find goto of I. That is already we have identified closure. For each element in this particular closure of S dash tends to dot S, we find goto of I, that is nothing but the state I. For the each symbol X, it may be a terminal symbol, it may be a non-terminal symbol. So which will take you to a new state. So that will be added to this particular C. So this particular C is nothing but canonical collection of item sets. So that is nothing but each state will represent a state in a DFA, which gives a DFA which will tell us from which state to which state we are supposed to move when a particular symbol is in red. Of algorithm, I'll show you how this canonical LR of 0 item set has been constructed. So you can just observe that you have started with this I naught, that is E dash tends to dot E. So you have added this, all these becomes the LR of 0 items. So once you complete this, you did using this on go to statement. Once you do this go to statement, it means that go to of E dash comma dot E, that is whatever the symbol you find after the dot E, you will find E. So you're going to use go to of I naught on E. It will take you to the next state, that is E tends to E dot, E tends to E dot plus T. That is a new state you're going to get. Similarly for T, you get E tends to T dot, and then one more T tends to T dot star F. That becomes a new state. Similarly, go to of T on that is I naught on F, which will take to the T tends to F star, and go to of I naught on open parenthesis. It will take you to the F tends to open parenthesis E dot E close parenthesis. Since E is a non-terminal symbol, we have added all the productions of E. Once again, we have added all the productions of T. We have added all the productions of F. This is nothing but closure. So once you get a new state, similarly on F from I naught, you are going to use go to of I naught on ID, which will be taking to the F on ID. It is nothing but, so you are going to use go to on I naught on E, I naught on T, I naught on F, I naught on open parenthesis, I naught on ID. You are going to get these new state, that is I1, I2, I3, I4, I5. Once again, once you get this, once again from this I1, so there is a transition on plus, that is I1, go to of I1 comma plus, so that is go to of I1 plus I1 comma plus, which will take you to the E tends to E plus dot T. E plus dot T. You can just observe that E plus dot T. Since T is a non-terminal symbol, we're going to add all the productions of T. Once again, we will add the productions of F. So it will be continuous. So you will get a new state. Similarly, you do it for I2. That is go to of I2 comma dot star F. So you are going to consider I2 comma star. So when you take I2 comma star, so you are going to get a new state called I7. What is your I7 will be? So it is nothing but T tends to T star dot F. So once again, F is a non-terminal symbol. I'm going to add productions of F into this, that is F tends to dot open parenthesis E close parenthesis F tends to dot ID. So then it becomes I7. There's a new state. So similarly, so when it comes to I3, there is no transition is required because after dot you don't have any either the terminal symbol or a non-terminal symbol. Similarly, when it comes to the I4, so you have a symbol that is dot E. So I will have a new state on I4 on E. What is I4 on E? You will get. So I4 on E, you get I8. That is your I8 is nothing but you are going to get, that is F tends to open parenthesis dot E dot, because you're going to read E from this E dot. Since dot followed by will have a close parenthesis, a terminal symbol, you want to add any more production to this. One more production with having E here is E tends to E dot plus T. Once again, E tends to E dot plus T. So this is your I8. So it means that, so you need not to add any new state if already the state is exist. So I8 is a new state. So similarly, so you have completed E here. Now you're supposed to consider E dot T. So E tends to T dot. So just find out whether you have any state with having E tends to T dot. So E tends to T dot. You don't have any, you have any production E tends to T dot. So you have E tends to T dot. It is already there. And then one more production T tends to T dot star F. This already exists as I2. You need not to create a new state for, once again, for this I4 on T. You can easily go from I4 on T, it goes to I2. Similarly, so you have completed T, you have completed E. Now you're supposed to see T tends to F dot. Do you have any T tends to F dot? So when you have T tends to F dot, that is once again, it says that I3 is already exists. T tends to F dot is already exists. So you need not to create a new state. Similarly, F tends to open parenthesis dot E close parenthesis. You can just observe that whether you have any state which is having the same thing, that is open parenthesis dot E close parenthesis, it is same as I4. You can just see that it is same as I4. So that's why we are not going to create a new state. Similarly, F tends to ID dot. So you have any state F tends to ID dot. So F tends to ID dot is nothing but your I5. So I5 is already exist. You need not to add new more state. What you need to do is from I4 on F, it goes to the same state. I4 on ID, it goes to the state I5. So this is how we continue to do this. So we get new state, we keep on adding the new state. If not, if already the states are exist, we use the same state. So we continue with the same state. So this is considered as a canonical collection of LR of 0 items. So this is also called as a transition diagram, which gives me information about from which state to which state I'm supposed to move. So using this, we're going to construct the parsing table. Now I'll stop it here. You have understood how to construct the LR of 0 item set. Then I'll be explaining about using this, how to construct a parsing table.